focus. Yep. Okay.
We have started the recording. Sorry.
Yeah.
I forgot to do.
And so we can, of course, get into details. So today the webinar is the ASINA webinar is related to the decision support tool for the safe and sustainable by design solutions. I put in brackets sustainable because ASINA project addresses a call in which only safe by design was required, but indeed we provided also sustainability performance indicators within the analysis. So my proposed outline of the presentation is this one. So the motivation, introduction of ASINA Expert System, and within the safe and sustainable by design framework, and its contextualization within the case studies then that we started investigated within ASINA project. Then the ASINA Expert System workflow and the data generation, the key decision factor and key performance indicators, and then addressing safety issues according to different perspectives. I provided you some highlights on ASINA Expert System architecture and features. And then we have some, we have two movies related to the user experience by using the platform, which is providing safe by design set of solutions, and some ASINA case studies that, well, participants present in this audience know, but we can get into some details if necessary. And then finally, ASINA Expert System impacts, requirements, limitations, and plus points at the present state of the art. So if you have any specific requirements within this set of topics, please, you can already indicate me what is most interesting for you. If there are no specific requirements so far, I will proceed according to the outline list of topics. Okay. So for the moment, I proceed. And yes, what is ASINA Expert System? Expert System is a quantitative-based decision support tool for multi-optimal, safe, and sustainable by design solutions. Quantitative because, as you will see, we address and we want to obtain figures, numbers out of different way of generating data. And the tool is a support tool, it's not the decision. It doesn't decide for the decision maker, but it supports the decision maker in having clear vision of what what consequences may be implied by specific decisions. Okay, this is quite important. And then a specific routine or module that you will see in action really provides support to better discriminate and select which one of the sorted safe and sustainable by design candidate solutions may be chosen by the decision maker, humans. Okay, it's a human-centric approach. It's a multi-optimal because, of course, it has to deal with different key performance indicators and different key decision factors, which we will define in detail by providing examples. So how to get the results, so how to sort the best candidate safe and sustainable by design solutions? Well, we implement a multi-objective optimization algorithm, which is part of the multi-criteria decision analysis. And this algorithm simultaneously maximizes or minimizes, means selects the best addressed KPI values, taking into account all KPIs at the same time. This allows to shorter the time to market in terms of development of solutions. So we'll comment this in the end. this scene applied to the research activities as they are, but also to possible industrial development of nano-enabled products. Then, as mentioned before, this is a quantity-based decision support tool, and it addresses 4 dimensions, which are basically environmental impacts, costs, so economic impacts, technical performance, and safety. By specifying the design requirements through this analysis and through the use of the DST, decision support tool, we are provided with a set of candidate solutions for safe and sustainable by design. The ASINA Expert System can address different life cycle stages and possibly interconnect different life cycle stages throughout the life cycle of nanomaterials, from synthesis to incorporation, use phase, and end of life options to be considered. For each life cycle stage, a functional system is identified, is defined, and within this functional system, key decision factors and key performance indicators are specified in advance, as we will see in a few moments. So just to give you an overview of the general workflow and which kind of data are generated through the process, we have, the life cycle phases. In this picture, we selected one of the possible, so incorporation phase, for instance. And this implies the modelization of the incorporation process, and to identify the variables in the recipe and in the units, processing units recipe that will potentially impact on different impact categories, which are related to different dimensions, like the environmental, the economic, and safety dimension. Here, we find out experimental characterization and quantitative data generation, which, of course, refers somehow to the physicochemical characteristics of materials or functionalities, address functionalities, which can be measured, or, as you see in the last block, the safety assessments addressed to the specific life cycle stage. So, for instance, in this case, we could address workers' exposure to airborne nanoparticles if we are, for instance, spray coating some nano powders, solutions or suspensions with nanoparticles inside. This is just an example. So all these data that are collected at the different levels, including modeling, this say LCA, for instance, and costing analysis is pertaining the modeling part, then those data will be harmonized and verified in order to assure findability, accessibility, interoperability, and replicability of data. Those data, or the data related to the collected data, sorry for replicating, are sent into the system, so the ASINA Expert System. So we are providing data which are then analyzed in the ASINA Expert System kernel, which is the solver or the safe and sustainable by design solutions, and will provide data to the user. Please take into consideration that often, cases are already been analyzed. So this means that you find in the database already analyzed data or raw data, input data for case studies analysis. So, of course, the ASINA Expert System allows you to select among the pool of existing data. You can upload again, you can recall, and maybe to integrate with new data for further analysis or for combining some life cycle stage with other life cycle stages. Okay, this is the more specific workflow, which allows us to see how to use at best the ASINA Expert System. So as you were appreciating from the previous slides, ASINA Expert System without data cannot work. So it's not generating data by itself. You have to pop in data, which are reliable and fair data, high quality data. So the higher the quality of the input data, the higher quality is the resulting analysis outputs that ASINA Expert System can provide. So first select the life cycle stage and then modeling the functional system, say a corporation, to stick to the previous example. Identify potential key decision factors like number of nozzles, for instance, or speed of the roll-to-roll tape, or, for instance, the concentration of the nanoparticles into the suspension, the flow rate of the carrier gas, which will allow spraying the solution, or the input power into the guns, okay, spraying guns, etc., etc. So we have, we may have in principle different key decision factors, okay? But, well, before taking into consideration all key decision factors, we have to select the ones that are expected to provide more impact to the KPIs, so the key performance indicators. That have to be defined, of course. So if we want to address the environmental dimension, which indicator we want to consider? The carbon footprint, or the acidification potential, the eutrophication potential, the ecotoxicity potential, or human toxicity potential, etc., etc. So depending on the kind of analysis that you are carrying out in terms of life cycle assessments. You can also consider all of the indicators by having a synthesis indicator of the environmental impact profile. But in any case, you will work with quantitative data to be analyzed. Then this part is related to the selection of the KDF. This selection may be carried out by experience of the incorporators, so the researchers or technical people that know very well their process. And, well, maybe there are some uncertainties, some unknown factors that could be checked by sensitivity analysis or previous preliminary screening of the cases in order to see what are the impacts on the KPIs, okay? So once we have defined the key decision factors and the key performance indicator, we may set the design of experiment matrix in order to, when this is done by defining, of course, the range of the selected KDF and for the selected KDF only. This will, of course, imply running experimental cases for obtaining data and also modeling. Can you see my mouse, or should I, oh, sorry, point with a pointer?
No, we can see
it's
it.
okay.
You can see my mouse, right?
Yes, yes, yes.
Okay, perfect. So this part is related to the modeling of the process, because once the process is known, we can model its impacts in environmental and economic. Epsilon stands for environmental indicators and gamma for impact, like cost indicators. Then the real set of experimental campaigns will provide nano-enabled products in this case, because we have fabrics, for instance, incorporated nanomaterials, nanoparticles onto fabric surface. And this is indeed a semi-finished product, but it could be already a product to put on the market, because you don't need to have a finished, dress or a bed linen or whatever. I mean, you have a functionalized fabric with specific functionalities. So let's consider this a non-renewable product for the moment. And well, during this campaign, you have also emission sampling, and you can characterize the functionality of your nano-enabled product, your fabric, which is spray coated with nanoparticles. You can characterize its properties in terms of fabric tensile strength, etc. If anything has been changed during the process, for instance. You can also run emission modeling and to provide ecotoxicity or toxicity assessments like oxidative stress on skin, etc., etc. So you are generating data, which are data from modeling, data from experimental campaigns, which are the basis for the starting point for the ASINA Expert System operation. Now, very important to say that this part, I get back to this slide, is quite critical part, because if you are not selecting interesting or relevant KDF, you may yourself somehow restrict the possibility to find safe or safer or safest by design solutions. So, well, it's also interesting before starting with the whole process of data generation to work on data analysis outside from experimental direct data that we are generating, and get to the literature, and out of this get some indications on which KDF might impact on some KPI. And this, for instance, within ASINA project, a TGO partner was in charge of that. And we can see, for instance, here, attribute importance related to the synthesis, in this case of nanoparticles, in terms of toxicity. So which parameter will mostly impact on this, for instance, KPI, safety KPI. This will help to select among KPIs which will be assessed, and this, of course, implies also physicochemical characterization of nanoparticles that will be synthesized. And in this case, in the synthesis analysis, this data will be ranked. Sorry, this KDF will be ranked in order to identify which is the most important one. I want here just to clarify that as an expert system may be used not only through the life cycle stages, but also at multi-level stage to simplify the analytical process by having a stage gate approach. So, for instance, we can run a shorter experimental campaign to identify the relevant values of the physicochemical characteristics of nanomaterials. And these can be considered KPIs of our experiment, of our functional system, okay? Then when identifying best PChem characteristics to be addressed, well, the KDF will be selected. So, for instance, physical chemical, for instance, zeta potential or whatever KPI will be considered. And then this KPI here, it becomes a KDF in the next level of as an expert system application. And then you can run the process as was detailed before until you get your KPIs. Okay, this is just to visualize the workflow and to get closer to the final results. So let's recall the experimental data, virtual data provided, which are a reference to the same design of experiment matrix. This is very important to have harmonized data. Pop it into the ASINA Expert System. What does ASINA Expert System do? Well, in this simplified 2x2 cases, yes, it's 2 KDF cases, you will get some curves in the decision space, which are, sorry, in the decision space here, which are connected to the performance space, okay? And then we will get back to this domain restriction concept, but I don't want to put too much concepts on the table for the moment. Let's step to the second part, which is the main concept of ASINA Expert System. So I was referring to the decision space, so the KDF, key decision factors. Within the key decision factor phase, you have DOA matrix, which allows you to somehow sample the decision space with real values and to get some functional approximation of decision space values. Then you're measuring the performances of your space, of your samples, for instance, and these are values that are within the objective or performance space. The issue here is to find connections between any point of the decision space and any point of the performance space. Okay, this is quite relevant because, by doing so, you can have a lot of information helping in the decision-making process. We will see how in a moment. Okay, I don't want to enter into this workflow, which is a little bit complex, but just want to give you an clear information that the data verification, so the fair data provision, will be enabling factor to feed data to the ASINA Expert System database. And only by these data could be analyzed. So this is a kind of filtering and harmonization process before, which is somehow necessary in order to assure reliability of the obtained solutions. Let's proceed on that. Then this slide, provides one of the first methodological attempts to address the safety KPIs. So to somehow assure that whatever will be the selection of the key decision factors, we will end up with a safe solution. This is a nice perspective and methodology, but sometimes it's lacking of metrics and of indications in terms of standards. So if we would be able to identify a threshold for the safety level, like cytotoxicity or oxidative stress level, etc., we would be able to identify this threshold, and we can say that if we are beyond that threshold, we have to reject any kind of design option. That would be nice, and this was the first attempt to address the safety factors, but sometimes is not applicable because this threshold is not available, and no one has defined or has enough indications, enough elements to define the threshold level. In this case, you find here two key decision factors and the response function of, say, cost function. Okay, you find here the cost level, which we want to minimize. Very good. We are lucky. We are in this point. By selecting the right values of the KDF, we can find a solution which is applicable in terms of safety, because you are in the safety domain. So the safety level here well, depending on how you define the safety KPI, but the safety level is above your point. Yeah, needless to say that if sigma is better, so the safety level is better if you have higher values, okay, well, this point and the minimum cost we have to reject. We cannot apply this design strategy, so design selection. So we have to be outside those circles. So depending on the situation and depending on the response functions that you find as a solution of your specific key performance indicator. Any question on that point? Maybe it's getting a little bit technical, but you can raise any question if it's not enough clear. I try to be clearer than I was. May I go on?
I think, yes, you can go on.
Okay.
Maybe in case of, just a note, in case of question, you can also write them in the chat and I will read it for you if you need, if you want.
Okay, thank you. Thank you, Federica, for monitoring this so that you can stop me anytime, okay? So let's see briefly the technical workflow, not the data workflow and the data flow, but how to use the ASINA Expert System. So we need, of course, an engine, as we were mentioned before. So the engine is the implementation of the multi-objective optimization problem algorithm, and you need a user interface, and you need a database to store data, which may be results or input data that you generate from the outer world. Important to say that when you open the area, your area in the platform, you are somehow allowed to indicate if you are working with a new case study or if you want to recall a previous case study analyzed. Previous case study analyzed may be partial because maybe you just address some PChem APIs without considering any environmental or cost impacts that now are available. So you can also include those data into the case study in order to have a comprehensive analysis of the safe and sustainable by design solutions you want to obtain. Well, two comments on somehow the evolution of the ASINA Expert System throughout its implementation. We work with a first version within ASINA project in which we had to perform the modelization of the functional systems and the analysis of the environmental and cost impacts before. Well, it's also possible to have these processes integrated within the ASINA Expert System. So having a system in which, by definition of the functional system and process, whether if it is synthesis or incorporation process of any kind, you can specify your design of experiment matrix and to obtain sustainability, economic and environmental sustainability outcomes in terms of KPIs. And this is attained by, of course, running the standard lifecycle costing and lifecycle assessment analysis through the process itself. So here we provided an example of the different steps that are implied in a process, which is a process in applying in cosmetic nanomaterials incorporation, and all sampling of the process is done, and recipe parameters are popped into the design experiment matrix, and you can get the LCA and LCC process through a virtualized analysis. This is the workflow of the ASINA Expert System in detail. So as we were commenting in the first version, we had the visualized synthesis external to the ASINA Expert System. And then we could select as a first step when recalling the ASINA Expert System which kind of situation we are in. And this is to clarify, the situation is defined by the amount of key decision factors and amount of key performance indicator we want to consider. Then we have the input module, which will allow us to input data either by popping data into one by one or by uploading through a template. Then we have a pre-normalization module. We generate the response function and we normalize again. And then we run the kernel, so the multi-criteria decision analysis task, which is the multi-objective optimization problem solving. And we are able to interconnect decision and performance spaces and, well, to run the block conversion module, which allows us to start from the performance levels, and this module allows us to get the key decision factors connected to those performances we want to address as safe and sustainable by design cases. And then the HMI as it will work. So we will see it in operation in the movie. The second case is the one I explained, in which virtualization is within ASINA Expert System. This, of course, implies to develop dedicated modules for the specific functional system to be analyzed. This clarifies one point, that ASINA Expert System may grow as a system in terms of data and of modules, which will allow the decision maker to run different design cases with a wealth of available data as a starting point, and also with enabling modules that will allow to virtualize the experiments to get environmental and economic impact data. This is the workflow, seen from the user experience. So HMI input, selector of the life cycle stages. If we are locating our analysis within a synthesis phase, which is the first phase, or to the incorporation phase, or if we have data related to the use phase, for instance, testing of fabrics through their life cycle, through the maintenance cycles by washing, and to assess the amount of leachate that could be collected out of the washing operation, and to identify the amount of potential nanoparticles into the leachate. Then selection from library of available design case studies. Okay, this is what I mentioned before. If you have available preliminary study case data, you can include. The decision of the number of key decision factors and KPIs, definition of the label attribution, so naming of the KDF and KPIs, and of course the unit of measurement you are using in the analysis, and finally the input data step. And this is what the ASINA kernel produces as a workflow. So decision on best surface fitting module. So this is the somehow mapping of the decision space and performance space. Check availability of enough safety data related to the design of experiment, physical chemical safety correlation modules. So we are able to interconnect physical chemical features with the safety outcomes related to the special features of the nanomaterials, and then to manage the experimental uncertainty or the input data in terms of uncertainties of the output data we are generating. Okay. Then, of course, the model for analyzing different safe and sustainable by design solutions. The availability of managing discrete and continuous variables, either as KDF or KPIs. Responsibility module and pre-normalization and back conversion model I was showing you in the chart, in the previous chart. Important to say that we have also the possibility to capture non-linearities in the behavior of the system. So the KPIs may be non-linear functions of the KDF, and the ASINA Expert System takes this into account. This is very important because it's a kind of unique feature, because most of the DST tools work with linear approximations, or at least at first order linearities. Then we have graphic outputs, and we have some options in selection and saving modes of data, like a table mode or graphic mode, and we have outputs to be printed. This is the first, say, page in the platform that you are shown when starting an analysis, and you see that you can select synthesis, use, and incorporation on end-of-life solutions. So the use case definition, you can recall available use cases, you can define a new case study, etc., etc. This is, but I don't spend too much time in this. You will see in the movie. This is the new interface that we recently developed for data input, in which you see here 2 columns related to 2 KDF and 3 columns for the 2 KPIs, just to simplify and to exemplify the situation. And these are the kind of outputs that you are able to obtain after the ASINA Expert System interpolation model produces. So you have a visual output on how things go when you are selecting some values of the KDF for different, of course, KPIs. I think that we can go through a user experience. So I would like to show you a movie that will visualize better what I was trying to explain you, maybe in a more technical language. Is there any questions so far before starting with this part? No, I see that Federica is not stopping me, so let me try to make the movie link work. So I try to, okay, I have to move, sorry. Did you see it here?
Yes.
Okay, great. So this is the first screen to log into the platform, and then we are just driving to we cut the movie, of course, it was too long. This is the list of available analysis. You define a case name, of course, the design case description, and textual data. You, of course, have to provide the date of the analysis, and you can work with different variables. In this case, we have 2 or 3 variables as a selection per case. So these are the KDF, which I was mentioning before, and you may have different key performance functions. Now we show up to 5, but it's basically indefinite number of KPIs we can have. It just matter of waiting enough time that the server will work out a solution, and then you may select the number of points. The points are the specific data related to samples generated, which may be, of course, the recipe corresponding to the recipe process recipe data. Here we are providing some values which are not really significant, of course. Then this is the resolution of your analysis. So by defining this number of points, you will get a more and more refined amount of data available, and more precise data available for your outputs, supporting your decisions. You can decide in this case if you want to maximize or minimize the key performance indicator, depending on what you're addressing. And yeah, you're asked to save the data input. The project is generated and put into the database. Then the kernel is working for some time. Just shorten here the time, lag time. And here, very interesting. Oh, maybe I want to get back for one. Too much. Let me try again. No. Okay. I wanted to stop in a specific screen to comment. Just a moment, let me try again. Okay, here. So basically, you can have any value in the performance space, or many. You can have any decisional value in the decision space. So the KDF, experimental KDF, are few, of course. You run a decisional experiment matrix with a few cases, and here many cases, I mean, infinite to the 2 cases are possible, because in any point in this domain you can have a case, but you don't know what are the performances of this case, and you don't know if the case, say 4.4, 2.5, this intersection will identify a synthesis case, but what are the performances that we are addressing? Okay, but more than that, are the performances maximized simultaneously? And the answer is no, because the set of multi-optimal, so multi-maximized KPIs are related to those points here. Okay, those are the sorted set of candidate, safe, and sustainable by design solutions. But even given this nice list of points, well, you don't know which one to, of course, select, because you don't know the effect. So the module, I think that will be shown afterwards, allows you to interconnect any point of this decision space to its related performance in terms of the 2 KPIs we are showing here. We took a 2x2 example to be simple, okay? Otherwise, it's difficult to have a exemplification. So, well, these diagrams allows you to really explore the KPIs in the KDF and to find out values according to the combinations of the key decision factors. And this, of course, works for all the KPIs. You can change the dimension, you can have screenshots for reports, you can rotate and really move within this space freely in order to investigate it at best, in order to clarify yourself what are the KPIs in terms of the decision couple of KDFs. You see here that you can, of course, yeah, this was a screenshot, so you can use this for reporting, for instance. It is quite useful. And the same is for the second KPI shown. But here, yeah, look at this. Now the decision maker selects one point. Oh, this is interesting for KDF 1 and 2, and you see that the red point was found. These are the interconnections. So the closest point, yes, provides the KDFs, which will provide you the decisional values here defined as X and Y. So you have a table. By selecting points in the performance space, you will be given back the recipe of the synthesis or incorporation process you will need to perform in order to get the expected key performances. You see that here, the decision maker investigates the space and makes considerations by maximizing or accepting levels of KPIs which are compliant with the design specifications. What I was mentioning before, if you imagine to have a KPI number 2 as a safety parameter, well, if you have a threshold, which a threshold that identifies the level which you cannot exceed, then that could be the right information on what are the viable safe by design cases the decision maker can select. But most of the times this threshold is not available. So the decision maker has to minimize as much as possible these safety impacts. Okay. So you can print a report after making your analysis, and you have here, you see here the table of the selected points and the KPIs that are shown in detail. Okay. So this is the value, and you can either select table mode or graphic mode to have a printout. This is just for user experience. So now I want to show you, if possible, another movie. Let me check if I'm able to find it. It was a quite fresh movie, so I'm looking at it for the first time as well. So this is a real, let me check. Should be here. Sorry, I have many screens open. I have to navigate in this messy monitor. Oh, here it is. It was hidden. So I have another movie here. Let's see. No, this is the old one, sorry. Maybe this is the one. Oh, I don't know which one. Sorry. I have to go a bit further. No, it was the right one. Sorry. Yeah, it should be the right one. So I skipped the first part. Okay. This is the loading of cases. Some modification of data, for instance. They change some values. This can be due to new experimental work or finding new average values, which are derived by more replica in the same experiment, and you are obtaining the results. Okay, so this is just to show you how it works in terms of collection of new data. Okay, let's move here. Okay. So we can now look at some case studies. Are we on time? Federica, how much time do we have here?
We have still I think half an hour. So I think
Half an hour. Okay, great. So at least few cases we can share as case studies that have been studied within ASINA project and with ASINA Expert System in its different evolution stages. ASINA Expert System, well, you may well know, is addressing two value chains, which are mainly impacting on different industrial applications, like photocatalytic filters for the first value chain, illumination system, and coated textiles with antimicrobial and depolluting properties. So, of course, textile antimicrobial and depollution is the photocatalytic application. The second value chain, which ASINA project addresses, is the cosmetic applications. And there are anti-aging and antibacterial skincare products to be developed by active nano capsules. So, well, now this is not the, no, I mean, we are in the first value chain. Sorry, this slide was indicating the wrong value chain. So we are addressing the first life cycles, the synthesis of nanomaterials in the first value chain. And we are addressing antimicrobial silver nanoparticles synthesis. Okay, this is correct. Recalling the previous slides, in this case study, we addressed environmental, economic, and functional key performance indicators. We considered two key decision factors and multiple key performance indicators within these three dimensions: environment, cost, economic, and functional. Sorry, I had to shield data for confidentiality reasons, because these are consortium data, but of course, since we are not seeing number, this provides you the clear vision of what has been done. We selected with, synthesis experts selected these two key decision factors, like the sodium hydroxide versus silver ratio, or weight, and the molar ratio of hydroxyethyl cellulose versus silver as the two main synthesis parameters. The synthesizer were CNR former ISTEC department and division, sorry, and they have synthesized those materials for quite a while, so they were very knowledgeable of the synthesis, and they wanted to investigate systematically the synthesis formulation to test against different key performance indicators, which were the PChem, physical-chemical characteristics of the nanoparticle. Well, here we have key decision. Sorry, you see here KDFs, but those are KPIs. Sorry for the mistype. All those are KPIs. So you see that we have multiple KPIs: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 KPIs belonging to different dimensions. So the first set is of physical-chemical KPIs related to the synthesis process and nanomaterials functionalities. And then we have economic KPI of the process and its inherent environmental impact based on the specific selection of the two key decision factors. Just for instance, if we look for the first point, which defines the first levels of sodium hydroxide, silver, and hydroxyethyl cellulose versus silver ratio, you will end up with specific carbon footprint data related to the CO2 emissions, and with specific cost per unit batch produced in connection to the specific physical, chemical, and antibacterial activities against E. coli and Staphylococcus aureus measure. So when we say that the ASINA Expert System is dealing with the quantitative-based analysis, it means that you need to have data, high-quality data that will allow you to perform analysis. This is the starting point. So ASINA Expert System is not called in yet, but when we call it in, yeah, we are able to provide the responses of the system, and of course those arrows indicate you that the aim of what we are addressing is of course enhancing the antibacterial activity against E. coli and to reduce the cost per batch produce of silver nanoparticles. And you can display those information out of the multidimensional space, which we cannot, of course, show as a diagram here, but we have to make projections on 2D spaces. The behavior of the system in terms of changing the selection. Okay. So here you have a different interconnection of the spaces analysis. This, of course, implied a little bit of work in order to find correspondences and to see where we were and to see what was the best solution to be applied. Okay, we don't enter into more detail. There was a solution within the upper high corner, which was finally selected as the best, safe, and sustainable by design silver egg nanoparticles to be further used in incorporation processes. Here we are addressing the incorporation phase. So in this perspective, you see that it's a stage gate analysis. So you first find out the best solution in terms of synthesis. Then we want to address the best solution in terms of incorporation process. And let's see what we worked out. I'm just checking the time. Okay, so in this case, we are addressing incorporation, and the two KPIs are the functionality and the safety index of the incorporation process. Well, as you can see here, we are addressing a quite common problem when we are making design an experiment or collect data which are not fully rationalized and planned from scratch, or if they are deriving from different sources. So data are not harmonized. You have a staggered mesh table of data, which corresponds to a incomplete or partial factorial or non-corresponding factorial analysis in DOE for all the characterizations. So you need to somehow harmonize and make a curation of data in order to enable their use into the ASINA Expert System analysis. That's what has been done. And this allows us to provide quite good interpolation of available data and extrapolation as well. We have to see here of the performance indicators, which are more than two. So we have two performance indicators for the functionality, the efficiency of E. coli and Staphylococcus aureus, and cell viability and genotoxicity in tail tests. We found out here, this is a sketch of the results. Well, this was 1 kDF. 1 kDF was the concentration of nanoparticles into the solution to be further used for spray coating activity. And as you can, of course, imagine the performance of the system was increasing by increasing the concentration of nanoparticles. Here as a safety, you see the cell viability, and you have a second here safety performance, which is providing an opposite trend. Okay, this is the interesting case to deal with, because if everything is aligned more or less, you point for the highest value and then you are done. You don't need expert system, you don't need analysis, everything is easy. But most of the times, real world provides us complex situation to be dealt with. And in this case, we have to identify the trade-off. So what could be acceptable? Well, in this case, we provided here the projections of different performances which are related to the key decision factors. This is to sketch that we found out that the best solution was that one, which I cannot tell in terms of ppm concentration, but it's a number obtained, and as you can see, was somehow contained in this range. Okay, this range was the goods range of safe and sustainable by design candidate solutions. And well, you see here in terms of normalized data, so those numbers in the y-axis are not referable to quantities, if not for the cell viabilities, which are expressed in terms of percentage, but the performances and other KPIs are in, say, arbitrary units. But this provides you the trend outcomes. Okay. So other case study, sorry, is rated the value chain 1 still for the incorporation phase, and this is the real application of nanoparticle suspension onto the fabric, and so to obtain really coated textiles. So second phase, what are the KPIs and key decision factors? Here we have 3 KDFs and well, it should be 3 KPIs as well. Sorry, this is type. We are addressing functionality. No, we are taking into consideration all of them. It's correct. So 3 KDF and 4 KPIs. Functionality, environmental impacts, cost of the process, incorporation process, and safety level of the process. The safety level has been addressed, I want to highlight, not in terms of nano safety, which was already addressed in the previous synthesis and in solution incorporation process, reprocess, but the safety in terms of human toxicity potential derived by the incorporation process itself. So here I want to highlight, you see that we are considering some safety parameters as part of the standard HCA assessment impact categories, and some of them are related to inherently nano toxicity or nano effects on human or environment. That's the limiting point of ASINA at that level, step of development, which is basically the state of the art in safe and sustainable by design at the moment, but this will be pushed forward in further scientific activities. This is the sketch, so the functional system, it's schematics, of course, of the process, in which we have the aqueous ethanol dispersion. So this was the one considered before. And then the pumping system, the guns that are able to spray on a roll-to-roll system, carrying out fabrics, which is was on this tape and moved through the coating volume. This activity has been performed by Senti partner in Portugal. And still, we cannot disclose the values of the flow rates and the roll-to-roll speed and nano particles concentration in the solution. Here you see the 3 KDFs I was addressing. And then we have these 4 KPIs in terms of silver nanoparticles deposited on the fabric, and the environmental impact indicator, which was obtained as a synthesis of the whole LCA impact categories, apart from the human toxicity potential, when it was considered separately in this analysis to address specifically and explicitly the safety level of the process. And so we end up here with the analysis of the three-dimensional, of course, outcomes in terms of X, Y, and Z. So you can recall the KDFs here. Sorry, X, Y, and Z are flow rates, rotor speed, and nanoparticles concentration. And here you have the the KPIs, and the KPIs provide in the performance space the outcomes. And since you want to maximize the KPIs, then you're able and free to select among the yellow color areas, which in the color scale provide the highest values. So yellow is hotter than blue, and then of course you are addressing these points. And the ASINA Expert System provides you which point in the key performance indicator space is related to the KDF. So this allowed us to identify the best options, the best safe and sustainable design incorporation processes. If we still have time, we can address the second value chain of ASINA Expert System, one of the cases analyzed, and this was the incorporation of nanocapsules. The synthesis of nanocapsules was already analyzed in terms of sustainability, of safety, and a specific nanocapsules formulation has been selected for the incorporation process, which is a turbo-emulsification process. Here I want to provide you this case study because this is a typical approach in which we can somehow optimize the stage gate use of as an expert system, because during the project development we had a limited amount of experimental cases to be performed because of time constraints and cost also of each test, and moreover duration of each test. So we wouldn't have been able to get all the full factorial experimental tests during the project timeline, so we had to design in advance. And in this case, we somehow provided a weighting of the pre-weighting of the KPIs, and we selected the ones that enable us to select the specific samples to be generated in order to further be tested into real products that have been lately produced by a RedOview company. This is the workflow of the simplified workflow of the turbo-emulsification process in RedOview. This is the dosage of part A of the recipe of the skincare product, and these water preservative chelating agents, humectants, and then steering of phase A, and then addition of the gelling agent and mixing homogenization, and finally the addition of nanocapsules that are active agent in the skincare formulation to get the anti-aging skincare cream. These were the KPIs that have been addressed, so the environmental, safety, and cost. So the two KDF, the decision factors that were selected by experts, turbo-emulsification experts, were the percentage, the amount of jelly agent, and the amount of nanoparticles to be considered in the formula. Okay. And this was done for different nanocapsules containing different active agents that were previously selected, And the analysis were done in virtual design and experiment mode in order to identify the best cases. And so we selected here, in this case, I want to share with you the coenzyme Q10 with vitamin E. And those are the points in the design and experiment, which of course spans the concentration of gelling agent and nanoparticles concentration as a possibility in the real formulation. So now we are addressing, of course, the incorporation phase, and we are addressing the KPIs OPEX, so the operational cost of the process and environmental impacts. So we have found here values related to the two formulations, and well, we see that of course the environmental impacts in terms of normalized values is minimal when we are using minimal amount of nanoparticles concentration, but we learn from this output that the amount of jelly agents is not playing a big role here. We don't have, well, it's a non-linear response that we know from detailed analysis of the outputs data, but we see a low dependence on jelly agent. So this could be one of the screening activities that could be done in order to see or to select the KDF that are relevant for the analysis. This was the same for the safety parameter in terms of human toxicity, and also related to the cost factor. You see that these are different, slightly different responses, but somehow aligned in trend. So not difficult to find out the best solution that could be selected. But important to say that, well, this analysis allowed us to restrict the dimensionality of the decision space to one dimension and see what could be the nanoparticles concentration effect on the other key performance indicator that were the functionality and nanotoxicity effects. So antioxidant performance was addressed in the second step of the analysis by defining a limited amount of real samples to be produced by the Redoview company in the incorporation process. And here are the results. Maybe it's not so clear, but I want to just show you that we have in blue the environmental parameter, the cost parameter in orange, yellow is the safety, and in green you find up here the functionality level. So the scale are not the same for all of them, but we can see that within this interval of concentrations, we can work quite easily, because all the environmental and safety performances are really providing good solutions. So we are minimizing cost and environmental and hazard for these products, but we are maximizing. We are already in a maximum level performance in this range. So that is a typical case in which we say, okay, under the industrial point of view, I can cope with 90% functionality instead of the optimum functionality I could get with the maximum concentration within the KDF range. But still, if I restrict myself into this range of 20-22 concentration of active agents, well, I will be fine, because the functionality is there, and we will get the minimal impact. As I was mentioning before, these scales are not the same. So the scale for the safety and environmental and cost, so economic indicators, are in normalized units. So 0 means the least value of impacts that you can find within the range. So it's not really 0, of course, it's a number, and this is in normalized units. So finally, RadioView selected really the best of best in terms of safety, because there was also other meta criteria to be met, which meant that if we were reducing the concentration of active agents, this meant that there were more freedom in playing with other ingredients like fragrances and so on and so forth. So this allowed them to have a better customization of the product in terms of regionality of application. So here it was the final selected case, and well, this was quite interesting as a solution. So we got what we were really aiming at. Final considerations, which are general, but I think relevant for the ASINA Expert System. So getting back to the tool itself, which is supported all this decision-making process within ASINA, also with the help of experts, which can be, of course, excluded in the process. So it's quite relevant. So human-centric approach, I want to stress this point. So expected impacts of ASINA Expert System. Well, and this is at the really beginning phases of this journey, I think. There is still a lot to do, but we already can envisage some relevant impacts in terms of technological industrial processes at all levels, not really only a nano-specific case, but also in conventional processes to address safe and sustainable by design solutions using safe chemicals, scientific research. Also, when scientists are synthesizing new materials, new nanomaterials, new chemicals, they may be supported in this phase in order to reduce their time for development. And then this may be also useful for generating data. The shorter the time for research and development, the higher the number of data available per unit time. So this is very interesting fact. So by gathering relevant data, harmonized data, that could facilitate a standardization and regulatory work. And then, of course, for material engineering in terms of industrial research for new products. Some highlights related to the expected impacts. Well, we are quantitative, but I want to stress the point that we are using the minimum and sufficient number of experimental samples. So experimental effort in terms of cost, time, and researchers in order to get relevant data to be analyzed to provide finally a good indication on where to go. So what could be the best synthesis or incorporation or use phase protocol or end-of-life options strategies and solutions. So the effect is to get knowledge of different design cases and to have a safety assessment which restricts the optimal cases to the allowed safe and sustainable by design one. So the points that we have seen in the movie are those restricted optimal candidate cases that the designer will select in the end. And this is a fast process. What are the requirements? Okay, ASINA Expert System doesn't work by itself. It's not a magic. It's something real. So it has to be comply with time, with cost, with resources, but at least you need to generate data, a minimal amount, but still a sufficient amount. You have to rely on experience in order to select the right number and type of key decision factors and range of the key decision factors. You need to virtualize, so to create a digital twin, somehow virtualization of processes in order to enable full factorial design of experiment analysis in terms of life cycle assessment, life cycle costing, and maybe social life cycle assessment as well, if you want to address another dimension in sustainability. Then running dedicated experimental characterization campaigns, this you cannot avoid if you want to work with primary data, which are reliable, so you need replica also. Sorry. And this allows you to also measure the physical chemical characteristics of your nanomaterials and the functionality that can display. So this allows us also to interconnect the PCAM and the safety and functionality levels of the final solution we are obtaining. Then running dedicated safety assessment and campaigns of like testing, viability test, oxidative stress, DNA damage, and whatever with the applicable test for the specific material and application. This has to be done. So selection of test is also a relevant point in the requirements. And then limitations. The selection of KDF variation range has to be the right one. Otherwise, we are investigating the wrong domain in the decision factor space. So we have to have conscience, and we have to be clear in mind what we are doing. If the variability of the range within the decision domain is minimal, too small, then we won't find any relevant change in the KPIs, and so we cannot discriminate sample from samples. So this also has to be devised in a clever way. On the opposite, if the variability of the KDFs is too large, then we will get too coarse mesh in terms of sampling of what's going on in the decision space. So we need more and more data, or we have to select a better KDF range. So this has to be done based on human experience or on relying on previous acquired experimental data. Other limitations. So how to handle the limitations? So the selection of the KDF's variation range has to be the right one, as I was saying. Maybe running preliminary multifactorial DOE in order to get a feeling of what's going on, in order to get the refined DOE for final testing in all dimensions, and then identify the suitable KDF, and KDF variability is key in this early stage phase. Then possibly finer mesh may be required, and this means more data in terms of experimental data or virtual design experiment in terms of modeling. ASINA plus points. So we don't have only limitations and things to be taken care of quite carefully. We have important point is that on the contrary of most of the artificial intelligence approach, which requires a huge amount of data for training, and the well-known training set, here we don't need such high amount of data, which are not available anyway. Because if you're making research, you don't have the time and money and resources to wait for years in order to collect huge databases to train an algorithm. So in this case, we have to cope with a small amount of data, and this is the way we are addressing the problem as an expert system. So as an expert system, requires just a reduced amount, a minimal amount of design cases to be worked with. And this turns into the minimizing the development time and cost of research or of industrial implementation. So shorten time to market, as I was mentioning before. As an expert system is a quantitative-based tool, so it allows to make comparison within the cases that we are studying, but recall that we are measuring the KPIs. So we can compare our data with our other, external literature data that are heavily measured by other groups with the specific and declared methodologies. The MCDA application allows us to merge all this wealth of multidimensional key performance indicators into one step analysis that allows to get safe and sustainable by design solutions, which are, I want to stress once more, relative to the specific case study, but still comparable to other external cases. So we are also always able to refer to external benchmarks in terms of products available or nanomaterials synthesized already by big groups like companies, Degussa or whoever is providing nanomaterials for the industrial world. The suggested SSbD solutions may be compared with other other solutions, as said before. Then, very important to say that this is a scientific implication. So when we are able to deal with the physical-chemical data, this could be considered not as KPIs, but as KDF. So key decision factors that are somehow connected to the key performance indicators in terms of safety or sustainability. So by addressing specific sizes or physical-chemical properties of the nanomaterials, we are somehow implying specific outcomes in terms of safety levels of hazard. Sensitivity is possible to be controlled by the ASINA Expert System by uncertainty propagation, which includes the numerical uncertainty propagation and experimental uncertainty. So we are able to control the outcomes of the solutions, which also may turn into no information. As I was mentioning before, is the discrimination between different samples in terms of KPIs is too small, then if it is too small with respect to the uncertainties of each sample, well, we cannot provide any answer. So this is also a guideline in order to identify better the KDF range. We can deal with continuous and discrete KDFs. So this means that, for instance, we can compare different materials considered as a discrete KDF. So material 1, 2, 3, 4, etc. We can compare nanotitanium, titanium silica, for instance, or silver HEC or silver CUR as antibacterial agents, and which one is the best one, and in terms of functionality, which one is the best one in terms of low environmental impact, etc., etc. So everything of this kind can be managed by the ASINA Expert System. And well, the quantitative results may also be discretized and to provide rankings. So we don't need to provide numbers in the end necessarily. We can provide values which could be viable, critical, or you cannot apply by defining some ranges within the continuous values obtained by the key performance indicators. I'm almost close to the end. We make simultaneous comparisons of different performances. This simultaneity is very important because this allows you to avoid the weighting of the KPIs. So which indicator, which performance is more important than others, you can decide in the end. Most of the processes requires you to cut off at the beginning some options because you are selecting some KPIs more important than others. Last but not least, non-linearities are taken into account by our algorithm, so you can really work out non-linear solutions up to second order factors interactions. And we solve also non-complex problems. The response functions that I will show you for the cosmetic application, it's a typical example. So this was also applicable. If available, we are able to set thresholds and options to the design technical specification and safety specification of our design case study. And yeah, the weighting procedure at the end is quite novel solution. So I can end up here, I think, almost on time, 4 times later than scheduled. Sorry for that. Hope that you are not sleeping like this nice pair. Hope that they will still keep to be in their environment if the climate change will not avoid this. So available for questions or for greetings, whatever you want. I see that also Davide is present, so happy about this. See you to all of you, and thank you for your attention.
So, okay, I think that if you have some question, I think that this now is the moment. In the chat, there are no questions. So I don't know if you have time if you want to ask something, now is the time. Anyway, I will, we can just say hello to everybody. Maybe we can wait for some moment. And anyway, thank you, Massimo.
It was too long, maybe talk too much and left a few space for questions. Sorry about that.
No,
I was trying to rush a bit because it's so many slides. And
so we have one question. Said, when will the platform available from Araceli? So when will the platform?
Okay. The platform basically is in many modules is available. We are now finalizing the last maintenance and the last update, because you have seen, I mean, people in ASINA have seen the old version interface. Now we are developing the new one, which allows you to work with the diagrams better, as you have seen. And we are, of course, available to have demos or to show case studies. Well, by soon we have to finalize this for the ASINA end of project, well, in 1 month or so. So we are quite confident that the platform will be ready for for use.
Okay, so
non-experts.
The use will be.
I mean, experts from the nanomaterial side for sure, but non-expert in terms of developers or IT people, which is not easy to find out the right way to have a good interface that could be somehow user-friendly. And well, in terms of data, we could work out this correspondence in huge tables. This could be done by, of course, scientists, but if you want to have a faster and easy to use tool, I think it's better to have some module which allows you to work with the mouse and to select points. And this was not really easy to implement in terms of IT effort, but it's done. So yeah, ready to go.
Very good, very good. So it's always something new to learn. So you can try to solve it by yourself, even if you're an expert. You can become an expert in using your platform. Who knows? Anyway.
Yes, I mean, as long as data are available. So if scientists already popped in data analyzed in the database, you can always use those data as just a bare user, recalling, say, the material characteristics of what you want to achieve, and then to have a clear indication on how to run a synthesis or incorporation process, if you're a synthesizer, or if you will just incorporate the nanomaterial into your substrate. Could it be a polymer or a metal flat sheet or fabric, technical textile or cotton, PP blend or whatever, and obtain results that could be then, of course, verified for your application. But as long as more data will be provided to the database, of course, as an expert system will become a real valuable tool in order to fastly direct non-enabled product designer towards the right path in order to get the targeted results in terms of function of multifunctionalities of their products, including safety, of course.
Okay, so thank you, Massimo. I think that if no more questions are in the chat, I think that we can say hello. We can say hello to everybody, and maybe we can keep in touch for the last ASINA webinar that will be on February 16. Okay, about the digital twin of developed within ASINA project. So thank you, everybody, and have a great day and weekend.
Thank you. Thank you for your time, for the participation, and thank you for organizing this, Federica.
You're welcome.
Best wishes to all the group of angels consulting.
Okay, so bye everybody.
Bye everyone.
Thank you.
Bye.
Bye. Thank you, Marcel.